Good day, folks. Welcome to Praise Mind Academy, where we bring brilliance to every lesson. Now, in today's video, we're gonna be introducing now a topic or a chapter called what internal resistance. This chapter it is not difficult at all. Trust me, it is not difficult at all. Now, it is just a little bit thingy that we are introducing what internal resistance. Now, we are just used to this resistance here, right? That is connected in series or maybe connected in parallel, right? So basically we call those the external. We call them the what? The external resistance. Why? Because now they are outside of the what? Of the battery, right? Now another important term I'm gonna add now it is EMF. Yes, you've been hearing of EMF, and yeah, you know that EMF it is the maximum battery. Sorry, it is the maximum energy that a battery can supply per coulomb of charge, right? Yes, that's the definition of EMF, the maximum energy that the battery can supply per coulomb of charge passing through it, right? Now, basically, the concept is that when you buy a, let's say now you buy a 9 volts battery, right? Yes, let's say now you buy a 9-volt battery. Now that battery, when you buy it, it is written 9 volts outside, right? Yes, it is written 9 volts outside. But the actual fact is that when you start, let's say those batteries you use them in what a remote, right? Let's say you use them in a remote, they're off. Now the minute you just put those what those cells or batteries inside your remote, when you just start using them, they do not give out the 9 volts SCDs. 9 volts SCDs. What happens is that due to the internal resistance that we will go into further detail with regards to, consumes some part of that battery because now it is a resistance, it is a resistor, Leona, right? So it should also take some voltage there, or therefore maybe the voltage that will be supplied to that will be used by those batteries and the remote will be more or less something like, let's say, 8.5 volts. Now the question is, or if you were to measure, but the question is, where is this point 5? Where is the point five volts thereof? That's when now we say now there is what? There is internal resistance. That's where it comes, right? And have you realized that after our batteries has died, maybe what we like to do, what we like to do is that we take those batteries and we chow them like, sorry, we just our stuff restuffing the batteries like we chow them with our teeth. Why? It is because now we want that a battery that is still inside, that little bit energy or power that's still inside the battery to do what? To be used up, right? So we are still fighting for that 0.5 volts that was lost, all right? That we did not get a chance to use it. So we rather do what? We bite that battery so that it can actually we assume that when we bite it we're gonna transfer all the energy and charge and what all right. Yes, now let's explain this in a more practical way. Now here is our cell, right? Here is our cell. So we know that our cell our current moves from the positive to the negative, right? From the positive to the negative. But I want you to realize this. Let's say we start here. We start here. When we start here, going to that part, do you agree with me that I'm gonna come out of the source with an I total, right? I'm gonna come out of the source with an what? With an I total. But can you see that the first thing that the I total meets first, it is the what? It is the internal resistance, right? So it means now before we go anywhere, there will be charge transferred to the internal resistance, meaning now the internal resistance will have some voltage thereof, right? Will have some energy. Therefore, the total will leave the internal resistance, come here. Or actually, let me do this. Yeah, it's fine. I was still explaining it. Then here we still have our I total, in this case they're off. Therefore, let's assume this switch is closed. Then this resistor R is gonna have the total resistance also. Oh, sorry, total current also. and back to our main source. Now I want you to understand this. Now you understand that the resistance here takes the I total, right? So what we have is that we will have the internal resistance. I'm gonna come to this EMF part. We're gonna have what? Internal voltage. Sorry, I mean internal voltage. Why am I saying we're gonna have internal voltage? Because now there is a resistor that is internally within a battery, and there it receives the flow of charge also. All right, it receives the current. So it means what will be the V internal? The V internal thereof will be what? The current total. Sorry, the current total as well as the resistance. This R represents the internal resistance. You do not need to say R int. No, 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 no. This R automatically the examiner or the marker knows that you are referring to the internal resistance, right? Now, remember we said the EMF, it is the, let's say it is 9 volt, it is the maximum energy that the battery can supply per coulomb of charge, right? Now, but we agree that when we now have V internal here, remember now, this V internal is gonna consume some voltage from the EMF. So it means whatever this V internal is here. So this one is gonna be our V external. It reads the V external that will be coming here. All right? This V is gonna read the V external that will be supplied through all the components that we have in the external circuit. This is the external circuit. This part, it is the what? The external circuit. Then this one inside the battery here, we say it is the what? The internal circuit, the off. All right. Yes. Now, if there is a V internal there, therefore you all agree with me that the V external, will be EMF minus the V internal thereof. Why? Because now the V external can no longer be 9 volts. Why? Because now there is what? There is a V internal that is inside. It is also referred as V lost. Okay, because why? It is lost within the battery. That volts are lost within the battery. Now the voltage here, the voltmeter reading here, it will be less. The voltmeter reading here will be less than the EMF. Why am I saying will be less than the EMF even though it reads? No, it does not read the EMF. It reads the external circuit. All right. Why is it less than the EMF? Because now the internal, the other part or the other voltage of the EMF has been lost or has been consumed. Yo, this English consumed by the internal resistance thereof. So this is what we say V external is gonna be now. All right. Yes, I repeat, this V external reads the voltage of the external resistance thereof here. So in this case, it reads the voltage of R. Now I want you to draw a graph with regards to this. Now we know V external it is equal to E minus V internal, right? So we have a graph like this. Here we have I think it's current here. Then here we have the voltage in volts. All right. Now the graph that we have is a graph that's like this, more or less. Okay, let me just redraw that. Okay. Now remember I said remember EMF. Actually, EMF is going to be V internal plus V lost. Oh, sorry, V lost is the same as V internal. V external. All right. I'll prefer using V internal because now it refers to the internal resistance. All right. Now, when we make V external, because can you see that this V here, according to our graph, it is V external. They won't tell you it is V external, but they'll just say it is V. When I just know what it is, what? V external, right? V external, when we want to make V external subject of a formula. Remember our straight line graph, it is y, it is equal to mx plus c. So here, the c, it is current. Can you see? Then the y, it is y, v external, right? So let's just make v external the subject of a formula. It's going to be v external, it is going to be, then I take this v int into the other side, v int, like this, right? Right? Yes. Therefore, can you see that? But I know what is v int. V int, it is what? V external, I'm going to leave it like this. But what is v int? V int, I know it is what? Remember, I say v internal. V internal is the same as the current total multiplied by the internal resistance, right? So it's going to be what then? It's going to be I internal resistance. Let's just put it in a form of y is equal to mx plus c. So it's going to be v external. Sorry, v external. It is equal to negative IR plus E. So what do I am explaining this because this is very important, people. Especially when you're doing grade 11, you're going to do experiments based on V internal. I think now that you are introduced to V internal, but for grade 12, it is a must. I am so sure about it. I think in term 2, if you're not doing acid base practical, you're going to be doing internal resistance, all right? Or you might do it in September, whenever, all right? But even though you do not do it, just for enrichment, because they might assess it on exam. So you have to be safe, right? Yes. Now, V external here. Oh, now it is in terms of y is equal to mx plus c. Y, can you see that this is my y is equal to, this is my m, my x, then this is my what? My c. Remember what is c? C, it is the y-intercept. Remember, this is the y-intercept. So it means where our graph cuts here, it is where we find our what? Our EMF. I repeat, C, it is our y-intercept, meaning where our graph cuts at the y-intercept, you get our what? Our EMF. These questions, they like to ask them, what is the EMF of these? All right? Yes. Now, another thing now, I is going to be positive, basically. So I is positive. Can you see? Now it means now our gradient here, it is negative R. Bear with me. Our gradient here, it is negative R. Our gradient, it is negative R. Why? Because the current is positive, right? There's no, yes, there is a current that is negative, but here we just include positive values. Yeah? So uh, your M rather will be now what? This is your x. Sorry about that. I, it is on the x-axis. This is x, right? This is y. So this will be your x. I do not want to write it like this. It is not a way. But yes, I want you to see that this is your m, but it should be negative m or negative r, right? So let me just collect it here. I'm gonna say y, it is equal to what? V external. M, it is equal to negative r. X, it is equal to I. Then y-intercept, which is C, it is equal to EMF. All right? Yes. All right. So now, do you agree with me when I say M, it is equal to negative R? Yes. Yes. Why am I agreeing with this statement now? Because can you see that the slope here or the gradient here, it is negative? Can you see? Yes. So I couldn't just say my gradient here, it is positive R. No, why? Because now my gradient is less than 0 here. It is what? It is a decreasing slope, right? Yes. So hence I'm saying my gradient, it is what? Negative R thereof. I believe you are following. I strongly believe you are following. Yes, this is what we basically mean with V internal resistance and all of that. And the most popular formula is that, remember I said EMF, it is equal to V internal plus V external maybe. Then if you manipulate this, remember the V internal gets the R, right? The I total, then R plus, when we talk of V external, we are talking about all the other circuits of the, all the other part of the circuit, right? So they're gonna also receive the total. If needed to be shared, it's fine, but we are just talking about the total here. So it's gonna be what? It's gonna be I, but now R what? R external in this case. All right? Yes. So when they just say calculate the R external, you're gonna calculate the resistance of everything except of this one. All right? But when they say calculate the total resistance, when they say the total resistance, you include the R. I repeat. When they say R total, it's gonna be R external plus R internal. But if they just say R external, therefore you'll just calculate R parallel plus R series, or whatever the case that you have in that particular case thereof. I believe you are following. In this one, no R included. When we talk about R external, they are specifying to you exclude this R internal. Okay, because yes, we know it is there. In grade 11, they might say the internal resistance is negligible, right? And we did not understand that question, right? That statement, rather, we just carry on. We know that it is negligible means we can ignore it. So, yes. But in actual fact, we had the V internal. So, we had to tell you, assume that it is not there, but it is there. And now we now assess it thereof, right? Therefore, EMF it is equal to what? Can I factor this? Yes, we have I there. Therefore, the formula it is R external plus R. Remember, when you add, the order does not matter. So this is going to be the important formula that you're going to use. Okay? This is going to be important formula you're going to use, followed by this formula here. Why? Because this one, it's going to help you when you are interpreting graph. Sorry. When you are interpreting graphs, you're going to need this formula thereof. I'm not saying you only need it in graphs, but it is very important when you are dealing with graphs. This one, normal calculation, right? But yeah, it always works. Do not cram these formulas. Just know, sorry, just know that. Oh, and by the way, they do not give you this formula on your answer on your what do we call this one? On your, what do we call this one? On your back sheet. What do we call that back sheet? Formula sheet. They do not give you this formula, if I remember very well. But yeah, even if they do not give you, just remember E it is equal to V external plus V internal. What is V external? I R external. What is V internal? I R. Then you factor out I R upon outdated. You are done. You are done. All right. Yes. Today I'm not doing any calculations. It is a concept overview. All right. I'm just explaining the concept. Let me come back to the graph. I'm saying my graph. The formula is very important is this one. But how did we come with this formula thereof by concluding therefore this is EMF and M it is equal to negative R? I'm saying the formula says it is equal to what? V internal plus V external. Right? But I know the graph that I will be given here, it will be V. But that V they are referring to, it is V external. If they wanted to say it is EMF, they will have told you. Instead, they will have written E here, right? They will have written E. But it is V. But this V that they are referring to, the question is it V internal or V external? Now I'm telling you that this is going to be what? V external. All right, it's going to be the external voltage. Then this is your what? Your current total. All right, this is your current total. Therefore, if this is my Y and this is my X, in this formula, I'm going to remember this. I can say it is Y is equal to blah, blah, blah. But I want to make it in a form of Y it is equal to what? Mx plus C. Why Y is equal to Mx plus C? Because now it is an equation of this straight line thereof. Ne? Therefore, I'm going to say, all right, on my Y, my y. What is on my y? My y, it is v external. So I just want to make v external the subject of a formula because it is what? It is the one that is the y. Then I'm going to take this v internal, I'm going to put it to the other side. I have what? E minus v internal, right? But now one thing I can do, oh, when I reach this stage, v external, it is what I want, yes, in terms of it is my y, thank you very much. But now I want my x to be my what? I want my x to be my I. All right. How can I get that? Remember, I cannot manipulate E, but instead I can manipulate what? V internal. I am acknowledging this EMF. Sorry, this negative. I'm not ignoring it. Okay. So I'm saying, all right, V internal, I can manipulate it in terms of I and R, meaning I can use IR here, right? Yes, because I know V internal is total resistance, sorry, total current multiplied by internal resistance, which is small letter r, right? But okay, I know, all right, if it's like this, I'm happy I have I. But can I put it in the standard of y is equal to mx plus c? Yes, I can take this one. Remember, it goes with the negative part. Please do not do me so wrong. It goes with the negative part, and I just rearrange it and just put it in here so that we can have this. All right, and the EMF, I just take it to the other side because I just swap it. It's positive, right? So it's going to be negative IR plus E. Now, and I say to you, now I know this is my Y, right? And I'm saying this is your X. Can you see? This is your X. This is your what? Your C. Can you see from the formula? The question is, what is M? I cannot just say M, it is R only. Why? Because there is this negative here. All right. So I'm going to say, therefore, instead of saying M, it is just R. It is instead what? Negative R. And this graph also proves it that my resistance, it is wrong, it is negative. So my gradient, it is wrong, it is negative, and I'm saying my gradient, it is R. Therefore, my gradient cannot be positive. It is instead what? Negative. All right. Yes. Now, when I come here, I am not doing any calculations. I'm just showing you. I want to show you. Can you see? If we have an EMF here, EMF of 9 volts. Let's say we have an EMF of 9 volts, ne? And say, actually, let's just do calculations so that you can see basically what I'm explaining. Now, I won't do deeper calculations, right? I know this V here that is connected across the source, the voltage source here. It is measuring the voltage here of the 4 ohms as well as the voltage parallel. I repeat, this V, which is V external, it reads the voltage of the 4 ohms, the voltage of the 4 ohms here, because it is external, right? Can you see this is external? Yes. It also reads the voltage of the parallel. Remember, the voltage of the parallel is the same here. VR2 is the same as VR3. So hence we say it is what? V parallel instead. So now I'm saying now this V, it is equal to the voltage, sorry, voltage of R1 plus the voltage parallel. This is what this V reads. All right. Therefore, we have what? We have V internal here. And we know that V internal is going to be what? The current multiplied by what? By the internal resistance thereof. All right. Yes. Now let's just see. Let's just see actually what might be our. Let's say now, I create is our switch is open here. Let me see what how many. Okay. Can you see that this switch is open? Okay, listen to me very carefully. When the switch is open like this, there is no current flow. Can you see? There is no current flow. It means now if there is no current flow, there is no V internal. Meaning, I want this. Is open. If switch S is open, therefore V, this one, V external, can I just name it V external? it is equal to EMF. That's the only instance where this V actually reads the EMF. Why? Because now there is no internal resistance. Why? Because there is no flow of charge. There is no current flowing throughout. Therefore, if there is no current flowing, there is no V internal. Why? Because now, so that we can have V internal, we need an electric current to come and flow into this resistor and do what? And supply energy. All right, and supply charges in there. Therefore, if now we close it, if now switch S is closed, what happens? Now V external becomes less than EMF. It is less. Why? Because now there is, due to V lost or V internal, it is the same thing. Why? Because there is some voltage that is lost in the internal circuit thereof. You get what I'm saying? There is a internal voltage here. So it means what we'll read here will be EMF. This voltage here, which I call V external, will read what? The EMF, but in this case minus the what? The V internal. You get what I'm trying to say, Akir? Yes. This is what I've been trying to explain, that V external it is equal to E minus V internal here. Can you see? Can you see? Yes. So that's the concept of what? Of V internal. So therefore, let's say maybe here, let's say V internal, it is equal to, it does not consume much, right? Let's say it is 0.5 volts. And if it is 0.5 volts, it means our current it is 1. Therefore, let's say here it consumes 4 volts. Now, remember, or if this is 0.5, we all agree that here is going to be what? 9 minus 0.5, which is 8.5. So this is going to be the reading 8.5 volts here. Right? Now, if this is 8.5 volts and this is 4 volts, it means the voltage here is going to be 4.5 watt volts. Can you see that when I add this plus this, it gives me the what? The V external. Right? But when I add this plus this plus this, it gives me the what? The EMF. But I repeat for the last time, then I'm just moving on. I'm gonna do questions. When I add this V parallel here and this V series, they are my external circuit, right? So it means they wanna add up to whatever this V, because this V, I like to emphasize this V reads the V external, but I repeat this V reads the V external. So if this is the external resistance, if we have external resistors here, as well as the external resistor here. So whatever the sum of those voltages here, this voltage and this voltage here will be equal to the voltage external. But when I say this one plus the internal, the minute I say I include all the V external plus the V internal, I now get my EMF. So I get my EMF thereof. So yes, thank you very much, folks, for watching my my video under electric circuits internal resistance, to be more specific. If you are doing grade 11, please watch this video also. Why now? Because you are also going to do V internal. It's going to be assessed whether on final or in June or in September. It's going to be assessed. Okay, please take note that as of 2024, which is last year, from the year that I'm recording, they started introducing V internal in grade 11. All right, in our previous years, 2023, we went doing V internal, right? But now, when are you going to be exposed to V internal, and you might be exposed to what experiments, including what V internal. So please be aware of that and learn this V internal thereof. So thank you very much, folks. Let's meet again on my next videos, where we'll be doing calculations regarding what internal resistance. The previous video did not include internal resistance, but the following ones will include what? V internal. Hence, now I did what? I explained the concept before we answer the questions that will follow thereof. Thank you.